Alright, this is exam 1 for Physics 102, Spring 2011. It says an object has a mass of 2 times 10 to the minus 6 kilograms placed in a uniform electric field of 640 newtons per coulomb, which is directed downward. The object floats. What is the charge of the object? Okay, first of all, the electric field is pointed downward. Alright, so we have a charge here. There has to be the force due to the electric field is up, and then the force weight is down. In order for the electric field force to be up, this has to be a negative charge, so automatically that gets rid of C and D, so we're just going for A or B. And then to find out, we say QE, which is the force due to the electric field, is equal to mg, and we want to know the charge, so charge is mg over E. That is 2 times 10 to the minus 6 kilograms times 9.8 meters per second squared divided by E, which is 640. Gives me 3 times 10 to the minus 3.1 times 10 to the minus 8. That's coulombs, and that's the same as 0.031 microcoulombs, and as I've already said, it should be negative, so the answer for number 1 is A. Proton is accelerated by a constant electric field of magnitude 220 newtons per coulomb. Proton is moving in the same direction as the electric field. How far does the proton move in 1 times 10 to the minus 6 seconds? Alright, so we want to know what is x. X is equal to v naught t plus 1/2 at squared, but here it starts at rest, so v naught is 0. So we need to figure out what is A. Well, we know that the force due to the electric field, QE, is equal to MA. So we solve this for A. This is QE, the force due to the electric field, over the mass. The charge of a proton is 1.6 times 10 to the minus 19 coulombs. E was 220. And M for an electron is 1.67 times 10 to the minus 27. These numbers were on your equation sheet. It gives me an acceleration of 2.1 times 10 to the 10 meters per second squared, and then I just plug this in for the acceleration here, and so x is equal to 1/2 times 2.1 times 10 to the 10 meters per second squared times my time, which is 1 microsecond, 1 times 10 to the minus 6 seconds squared. And I get 0.011 meters. And that is D. Alright, this figure shows two charges and their electric field lines. The charge on the left has a magnitude of 6 microcoulombs, so it's plus or minus 6. Since the field lines are ending in this charge, we know it has to be negative 6. And so the other charge has to be positive. We count the number of lines, 1, 2, 3, 4, 5, 6 lines over here. There are 12 lines surrounding this charge, so it has twice the charge, so this is plus 12, that's C. What is the net force on the center charge in this figure? Okay, let's just first draw the force vectors. Due to this negative charge, has a force in that direction, and due to the positive charge, also has a force in that direction. Those forces, since it's equidistant between these two equal magnitude charges, are equal, so the force is equal to 2, because there are two 75 microcoulomb charges, times k q over r squared. That's equal to 2 times 9 times 10 to the 9th, 48 times 10 to the minus 6 coulombs, 75 times 10 to the minus 6 coulombs, divided by 0.35 squared. And we already know it's to the right, so we get rid of all these to the left answers. We also know it's not 0, and number 4, let's see, that gives us 93 newtons. So it's 93 newtons to the right. That's E for number 4. Which of these is not a valid charge? Alright, well, A, that's the charge of an electron. Negative 4 coulombs, that's just a lot of charges, as we talked about in class. 8 times 10 to the minus 6, times 10 to the minus 19 rather, that is, 5 protons. Because 5 times 1.6 is 8. And so that leaves B. If you do 7 divided by 1.6, this is 4.4 protons. You can't have that, so it's B. Consider this configuration of charges. Which vector best represents the net force acting on the rightmost charge? That's on this charge. Alright, so we have, let's just draw the vectors. Due to this plus 2q charge, I have a force vector that goes in this direction. And then due to the minus 4q charge, I have a force vector that is considerably bigger, more than a factor of 2 bigger. Goes in that direction. And so the sum of these two vectors, oh, by the way, this force vector is bigger. 1, because this charge is twice this charge, and then also it's slightly closer because it's on the right side of the triangle instead of the hypotenuse. So the sum of these two vectors will give us E. In this figure, two charges are separated by a distance d. The point A is equidistant between the two charges. The point B is distance d over 2 from the right charge. So A and B are both the same distance from negative 4q. Where is the electric field greatest in magnitude? So let's just draw the electric field vectors. Imagine taking a positive particle and placing it there and ask yourself, what is the direction of the force on that particle? Well, if I put a positive test particle here, I get a force in this direction due to this charge, and in this direction due to this charge. Now over here, I get a force in this direction due to the minus 4q charge, and then a smaller force in that direction due to the plus 2q charge. Now these two vectors are the same length, and so the one with the largest electric field then is at point A. Number 7 is A. Which best describes the work required to move the charge along the dotted line in this figure? Alright, well, there is no change in potential because this is an equipotential line. Work is Q delta V. Alright, you can also think of it as that the displacement is at 90 degrees to the direction of the force due to the electric field. So it requires zero work. This figure shows how particles A and B respond to each other, and separately how A and C respond to one another. Which of these statements is true? Alright, A and C are opposite charges. A and C are opposite charges. That's not true because these two charges are repelling, so they have to be like charges. B and C are like charges. Let's look at these others actually. A and B are like charges. That's not true because they're attracted to one another, so they're opposite charges. Now, if A is attracted to B, so let's say that A is positive, then B would have to be negative. So if A is positive, then C would have to be positive. So B and C then cannot be like charges because of the way they act. So B and C have to be opposite charges. Proton and electron are in a constant electric field as shown. You release an electron and a proton at a point equidistant between the plates. Which particle has more kinetic energy when they strike the plates? Alright, well, they're both going through the same change in potential, and they both have the same charge, so they both have the same kinetic energy. That is A. Two charges are arranged on the vertices of the equilateral triangle. If Q is equal to 2, what is the potential at the top? Alright, so here we have 4 microcoulomb charge, and here we have a minus 8 microcoulomb charge. You just say V is equal to the sum of KQ over R. So that is K times 4 times 10 to the minus 6 over 1 plus negative 8 times 10 to the minus 6 over 1, and putting in K is 9 times 10 to the 9th, I get negative 36,000 volts. That is D. You could also make this slightly easier because you see half of this charge, since it's equidistant from this point, cancels with this charge. So I could also just say that V is equal to K times negative 4 microcoulombs over 1, and that would also equal negative 36,000. Of course, this should be times 10 to the minus 6. Alright, but you didn't have to go that way, but you could. In this figure, the electron sits between two charged plates. The electron moves to the right in response to the electric field. What is the direction of the electric field? All right, in order to have a force that goes in that direction, your electric field has to be in the opposite direction because it's a negative charge. So the electric field is to the left. Which of the following diagrams is the potential on the x-axis equal to 0? All right, well this one, for example, only has negative charges, so it's not that one. This one, at the point here, this distance is smaller than that distance, and similarly these distances are different. Here, these two distances are different, and these two distances are different, so the potentials don't cancel out. So none of these have a potential equal to 0, so the answer is D for 13. Consider this figure. If Q is 1 coulomb, so we have 1 coulomb here, 2 coulombs here, and 4 coulombs here. How much work is required to assemble the charges into this configuration? Alright, well, let's take them one by one. The work here is equal to 0. The work here is equal to Q delta V. That is 2 coulombs, which is the charge that you're moving into place, times KQ over R. That's K times Q, which is 1 coulomb, over R, which is 2. Alright, so I'm just going to put this in terms of K, and then we'll come back. So this is just equal to K. And then the work for this charge is equal to Q delta V, which is 4 coulombs, times K times 1 coulomb over 2 plus K times 2 coulombs over 2. That's the potential due to this charge and this charge. Alright, so that is, let's see what we got here. 4 times K over 2 plus K. It's 1 3/2 K. That is 6K. So my total is 0 plus K plus 6K, which is equal to 7K, or 7 times 9 times 10 to the 9th. I get 6.3 times 10 to the 10. That's equal to 6.3 times 10 to the 10 joules. Alright, so that is C. Number 14 is C. This figure shows positive charges with concentric circles surrounding it. At what point is the potential at its greatest value? Well, V is KQ over R. So if R is small, that means that V is big. So at the smallest radii, points C and D. C and D are on an equal potential line, so they have the same potential, and that potential is the greatest potential. So that number 15 is E. What is the equivalent capacitance of this circuit? Alright, we want to begin with these two, which give you 1 over 1 over 4 plus 1 over 4. That's equal to 1 over a half, which is 2 microfarads. And then you combine these circuits, these capacitors, so you have a 2 microfarad here, and another 2 microfarad. That just gives you another 4 microfarad. So your circuit looks like this. You have a 4 here and a 4 there, and the sum of those two is the same as we did up here, so it's just 2 microfarads. So number 16 is A. For the circuit in the previous figure, what is the potential across the 2 microfarad capacitor? So I want to know what is the potential across this capacitor. Well, I have 12 volts here, and these two capacitors then will both have 6 volts because they're identical and they're in series. And since this capacitor is the equivalent of these which are in parallel, then this 2 microfarad capacitor is going to have the same voltage or the same potential, which is 6 volts. So number 17 is C. Consider the circuit. What is the charge on the 3 microfarad capacitor? Alright, we need to figure out what is the equivalent of these two capacitors. So that's 1 over 3 plus 1 over 6. That is, what's that? 2 6 plus 1 6, that's 2 microfarads. So that capacitor, these are the same as a 2 microfarad capacitor, and it has 12 volts across it. So the charge on this 2 microfarad capacitor is CV. That's 2 microfarads times V, which is 12 volts. That's 24 microcoulombs. So we have 24 microcoulombs across this equivalent capacitor, and since these two are in series, they share the same. So So the answer for number 18 is B. Circuit in the previous figure, what is the charge on the, oh wait, I'm sorry, let's see, what is the charge on the 3 microfarad capacitor? Yeah, so it's 24 microfarad. What is the charge on the 2 microfarad capacitor? So this is very similar. The voltage across this capacitor is 12 volts. So that charge is just CV. That's 2 microfarads times 12 volts, which is 24 microcoulombs. So the answer for number 19 is B. And it, by the way, it's just a coincidence that these two have the same charge, because capacitors in parallel don't necessarily have the same charge. It's just the way these worked out. Well, it's because they're the same capacitance. These 6 charges at the corner of an equilateral hexagon, what pair of statements best describes the electric field and potential? Well, for the potential to equal 0, you have to have equal numbers of positive and negative charges equidistant from the point. So we have 1, 2, 3 positive, 1, 2, 3 negative, so the potential is equal to 0. And then to find the electric field, we just want to draw our vectors. So due to this charge up here, our electric field is in this direction. Due to this charge down here, our electric field is in that direction. Due to this one, it's in this direction. Due to this one, it's in this direction. Due to this charge, our electric field is in that direction. And due to this charge, our electric field is in that direction. So the sum of those vectors is not 0. The net vector is actually to the left. So E is not equal to 0. So let's see, V is equal to 0, E is not equal to 0. That is B. Number 20 then is B. Capacitor consists of 2 metal plates with an area of 0.4 meters squared each. The plates are separated by a distance of 1 times 10 to the minus 6 meters, a micron. A piece of paper is placed between the plates. Dielectric constant 1.5. What's the capacitance of the capacitor? Alright, we're just plugging in the numbers here. Kappa epsilon naught A over D. Kappa is 1.5. That's the dielectric constant. Epsilon naught, or E naught, is 8.85 times 10 to the minus 12. A is given, it's 0.4 square meters. And D is 1 micron, or 1 times 10 to the minus 6 meters. Plug those numbers in, you get 5.3 times 10 to the minus 6 farads, or 5.3 microfarads. That's D. Parallel plate capacitor initially has a potential difference of 200 volts and then disconnected from the charging battery. If the plate area is now doubled without changing Q, what is the new value of the voltage? If the plate area is doubled, A is doubled, that means that C is doubled. And since we know that Q is equal to C times V, if we double C, keeping the charge constant, then our voltage has to be halved. Alright, so our original voltage was 200, our new voltage is now 100, that's A. Consider this circuit. What is the current through the resistor? Well, V is equal to IR. I is equal to V over R. That's 12 over 3, which is 4 amps. Which following best describes the purpose of resistors? They don't store electrical energy. That's for a capacitor. They don't turn a circuit on and off. That's a switch. They don't act as a timing device. That could be a capacitor. They slow the flow of electricity, or they resist the flow of electricity. That's D. And this is version B of the test. There are all the key